Hello, my name is Amin Qaderi. This is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. The title of my talk is Novel Neurocognitive Models Can Explore Spatial Attention's Effect on Perceptual Decision Making. Current results have been performed in collaboration with Jamal Amani-Rad and Michael D. Nunez. In general, these talks contain two phases. In the first phase, I'll show how spatial attention can shift the underlying process of a perceptual decision-making task. For this purpose, we compared 5 directed neurocognitive models to answer this question: which DDM's parameter is most manipulated by top-down spatial attention? So we use a public dataset to explore this question. In the next phase, I'll focus on introducing novel single-trial integrative neurocognitive models and evaluate them by parameter recovery and model misspecification. This is the theoretical presentation of the neurocognitive model for the study of the human cognition, which constrain and describe both single-trial neural activity and behavior simultaneously. In this figure, you see 3 types of decision boundaries: static, linear, and viable collapsing, as well as you can see 2 different EEG measures. The first EEG measure is M200 latency with a blue line at the occipitoparietal cortex, and the next is the centroparietal positivity CPP with a green line. These EEG data can constrain and predict latent parameters at the same time. The previous findings has shown that M200 waveforms can track visual encoding time and the onset of evidence accumulation. Moreover, P300 or CPP slope can account for the drift rate accumulation process. In this slide, you see the graphical representation of the neurocognitive models. Subfigure A shows the directed joint model, subfigure B is the traditional integrative joint model, and subfigure C is the novel single-trial integrative joint model. These 3 graphs display 3 different approaches for linking brain and behavior. Node Z is the EEG data, and node X is the behavioral data such as response time and accuracy. The double border node in the directed model shows parameters that are not estimated and deterministic. Shaded double border node in the single-trial integrative model refers to parameters that are not necessarily estimable and stochastic in simulation. That is the main reason that we have to use a simulated approach such as deep learning to approximate posterior. There are 2 main advantages of using single-trial EEG in comparison with the trial average ERPs. At first, single-trial ERPs improve the neurocognitive theories to estimate and constrain cognitive parameters precisely well. Secondly, there is valuable information across trials that influence cognitive parameters. The main disadvantage of the single-trial approach is that the use of the single-trial ERPs causes some noise and artifacts which is somewhat difficult to remove. We try to solve this disadvantage by applying singular value decomposition (SVD). In the SVD, we use spatial filtering to increase the signal-to-noise ratio for each trial. Nunez et al. Showed that the N200 latency between 150 to 275 after a stimulus appearance in the occipitoparietal electrodes could reflect the visual encoding time. Moreover, Connell et al. Identified the CPP represent the drift rate parameter. This graph displays a general overview of how to extract N200 latency at the single trial level and how they lead to predicting the onset of accumulation process. At first, we run SVD to obtain a weighted map for each participant and then use it to drive N200 latency for each trial. This figure shows that the EEG measure and cognitive parameters can be combined to describe and predict behavioral data. To explore the spatial attention's effect on a perceptual decision-making task, we propose 5 neurocognitive models in the context of the drift diffusion model. The alpha parameters is the bound decision, beta is the bias, delta is the drift rate, eta is the drift rate variability across trial, and finally for the non-decision time, we use the regression model R plus lambda times X. Model 1 says that the spatial attention cannot shift any of residual R and coefficient lambda parameters. And model 4 assumes that the both residual and coefficient lambda are manipulated by a spatial attention. We fit coherence to the delta parameter in these models because of a large number of relevant previous findings. You can see this preprint for more information and access to other models and analyses. This slide shows two diagrams of hierarchical Bayesian models related to the model 1 and model 4. Based on the model comparison criteria, you see that model 4 is the best, which means that the spatial queuing can shift both visual encoding time and motor execution time. We implemented these models easily in Python because we have likelihood forms. In this step, we propose some novel neurocognitive models at the single trial level. These new integrative models are better for inferring about individual differences and the trial-to-trial changes. Also, they can constrain and predict both behavior and EEG at the single trial level. The single trial integrative models are complex, so we try to use a likelihood-free approach to approximate the posterior parameters. The first set of equations is the main concept of integrative joint model. Behavioral data is called X comes from a joint distribution of gamma and phi. On the other hand, EEG measures that is called Z comes from the joint distribution of gamma and psi. You can see the gamma parameter exists in the both behavioral and EEG. That is the traditional integrative joint model, which is not related to the single trial level. So for this conventional paradigm, if we permute X and Z across trial, the same parameter estimates will be obtained. In contrast, we introduce a new paradigm at the single trial level. The second set of equations is a general paradigm to show that how to combine both brain and behavior at the single trial level. You see that the noise sense parameters lambda I on every trial are shared in the both X and Z. This model contains both behavioral and EEG data to each other at the single trial level. By permutation, different parameter estimates are obtained, so this means that this approach can constrain both modality at the single trial level. To recover true parameters, we have to use a likelihood-free approach such as deep learning. So common software like Python and JAX cannot estimate posterior of lambda I for each trial. Most likelihood-free approaches are case-based. This means that for a new dataset, all approximation steps have to start from scratch, so that is not cost-effective. Moreover, amortized Bayesian approach is a general approach that approximates posterior or likelihood for each arbitrary data. Fengler et al. Proposed MLP and a CNN to approximate likelihood, but the base fellow package is useful to approximate directly the posterior, which is proposed by Radev et al. We use base fellow for parameter recovery that has two phases. The first is the training phase, which takes a long time to train a summary and invertible neural network, and another phase is the inference phase, which takes less time and is very cheap. We constructed some traditional integrative joint models and then examined parameter recovery of each model. In this slide, you see two different models related to the N200 latency and CPP. Tau is a visual encoding time and tau m is the motor execution time, so you can see that EEG measures can constrain tau e. This model formulates a source of noise related to the EEG measures. The bottom model suggests that the trial-to-trial variability of drift rate comes from CPP, and also mean of CPP represents the mean of drift rate. That is a sample of integrative joint model at the single trial. The key benefit of this framework is that this kind of model includes at least one source of measurement noise for EEG data, which is called sigma, as well as variance in the underlying cognition that change across trial named S. This model also has a theta parameter that indicates how much of the observed data is contaminated with the uniform noise. For the model in the previous slide, we used base flow to recover the true parameter. Y-axis represents the posterior of estimated parameters, and x-axis represents the true parameters. This slide includes an integrative neurocognitive model that predicts CPP slope related to the rate of accumulation evidence variable on single trials. This model assumes that the trial-to-trial variability of the drift rate parameter at the model level comes from CPP variance at ERP signal, as well as there is source noise of CPP slope. We'll publish the preprint version of this paper with this title in the next few weeks. Moreover, we showed how robust the current models can be when explicit assumptions are contradicted. In general, we consider two types of model misspecifications. The first type is related to DDM simulator, so we use a contaminant process where 5% response time is generated by uniform distribution between 0 and 2 seconds. Secondly is related to changing the kind of relationship between EEG measures and DDM's parameters. We use gamma distribution instead of normal distribution in the relationships. The result of using different model misspecifications show that the current neurocognitive models are robust. This is the specific result related to adding 5% noise data to N200 latencies. You can see these references for more information. And finally, thank you for your attention.